So let R be a vector-valued function. We can define this S to be the integral from 0 to t of the length of the derivative of R. When we first learned about arc length, we used this function to parameterize by arc length. This function gives you the length of the curve from 0 to t that's traced out by your vector-valued function. We also have defined the unit tangent vector. So the unit tangent vector is the derivative of your vector-valued function divided by its length. This gives you a unit vector in the tangent direction to your curve. Together with the unit normal and the unit binormal vectors, they create a three-dimensional axis system that moves along your curve. If I take the derivative of both sides of this S function, the fundamental theorem of calculus says integrals and derivatives undo each other, and so the derivative of S is this length of the derivative of R. In this video, we're going to define a new idea called the curvature. So, the curvature of your vector-valued function is usually denoted with the Greek letter kappa, so that's a kappa there. It's defined to be the magnitude of your unit tangent vector, the derivative of your unit tangent vector, divided by the length of the derivative of R. Now, if you happen to be parameterized by arc length, so if it happens that the derivative of your vector-valued function is equal to 1 in magnitude, then the curvature kappa is simply the magnitude of the derivative of the unit tangent vector. This situation is where you trace out the curve at constant speed. So if this is true, then you have parameterized by arc length. Meaning that if you travel t seconds along your vector-valued function, then you've traveled exactly a distance of t meters along the curve. You're tracing the curve at a constant speed. The derivative has magnitude 1. Okay. This is the definition of curvature, but what is it telling us geometrically? Let me try to sketch a picture here. So here is a depiction of one curve described by a vector-valued function R. At different points on this curve, we have different unit tangent vectors. So I'm going to draw a bunch of unit tangent vectors to this curve. So a unit tangent vector is a vector that's length 1 and in the direction of the tangent to the curve. The curvature is measuring how fast the unit tangent vector is changing. So when you take a derivative of something, you're measuring how fast that thing is changing. So kappa is going to be a small number if there's not a lot of change in your vector-valued function. So in this region here on my curve, I would say kappa is small because the unit tangent vector is not changing very quickly. However, in this loop-to-loop portion, I would say that kappa is big because it's really rapidly changing the unit tangent vector as you whip around the curve. So the curvature measures how curvy your curve curves. So here's a theorem. You can calculate the curvature using the definition. Alternatively, there's a way that I prefer to calculate the curvature. The curvature is equal to the magnitude of this cross product divided by the length of r prime cubed. That's a 3 there. So let me show you why this is true. So let me prove this theorem. I know you're able to understand this. First of all, we have that r prime is equal to s prime times t. That's what we have right over here. So I could just take this definition of the unit tangent vector, multiply both sides by s prime, and we've got this relationship. So, taking the derivative of both sides, I get r double prime, using the product rule, is s double prime t plus s prime t prime. Thus, I could take a cross product. So, the magnitude of the cross product is equal to, let's see here, the magnitude of s prime t cross s double prime t plus s prime t prime. Whenever you take the cross product of a vector with itself, you get the zero vector. That's a basic property of cross products. So the cross product of a vector with itself is 0. So this is really the magnitude of s prime squared t cross t prime. The first cross product was 0, so I just wrote down the second one. Another basic property of cross products is that, so here I got s prime squared. Another basic property is that when you take the magnitude of a cross product, it's going to be this, the magnitude of t times the magnitude of t prime times sine of the angle between the two vectors. The length of t is 1. It's a unit tangent vector. By design, it has length 1. So that is 1. T prime is in the direction of the unit normal vector. So the angle between t and the unit normal vector n is pi over 2, or 90 degrees. Sine of pi over 2 is 1. So what we have so far is the magnitude of this cross product is equal to s prime squared, the magnitude of t prime. But because I'm trying to get kappa involved, I'm going to write this as the magnitude of t prime divided by s prime. And I'm going to change this to a cubed. Now, if you just write down everything we have, s prime is the same as the magnitude of r prime. So I have the magnitude of r prime cubed, and then this term is kappa. So I could divide both sides by this term and get the statement in the theorem. So that's why the theorem is true. Let's actually use the theorem to do an example. So let's find the curvature for the, how about vector valued function r of t equaling t squared and 0. This here is describing a curve in the xy plane. The third component, the z component, is 0. But I wrote it as a three-dimensional vector in R3 because I'd like to take cross products using this formula for the curvature. And you can only take a cross product in R3. So the curve I'm describing here is nothing more than a parabola. This says x could be equal to t and y could be t squared. In other words, y is equal to x squared. The basic shape of a parabola. So here's my vector valued function r of t. Let's find the curvature using this. So I have my function r. I will take the derivative, r prime. That will be 1, 2t, 0. The second derivative is equal to 0, 2, 0. So therefore, the magnitude of the cross product would be r prime cross r double prime. And if you take the cross product, everything's already lined up here. The first component of the cross product would be 0. The second component would also be 0. And the third component would be 2. So I'm taking the magnitude of this vector, which is clearly a vector of length 2. So therefore, the curvature kappa is equal to 2 divided by the length of this vector cubed. So the length of that vector is 1 plus 4t squared in the square root. Cube that, there's my curvature. So let's see if this makes any sense with our intuition that the curvature should be a small number when the curve is flat and a big number when it's more curvy. So if I plug in 0, let's see here, kappa of 0, if I plug in 0 for t here, then I get 2. So here at the value t equals 0, the curvature is 2. However, if I stick in 1 for t, I'm right here maybe, then the curvature is 2 over root 5 cubed, which I think is approximately 0.178, much less than 2, because the curve is a lot less curvy over here at t equals 1. Okay, so now we've introduced curvature.